So, hi everybody, thanks Eric for the presentation. Again, I'm Cristiano and my talk today is about live update. Sorry for everybody disappointed in not seeing fine-grained control flow integrity in Minix, but that will be for another time. Today I'm going to talk about live update. This is research effort of a few years. Andy mentioned this morning of the recent introduction of live update support in mainline Minix. In this talk, I'm going to cover the making of all that. Essentially, all the research we did over the years, which eventually culminated in the inclusion of live update support in the Minix release. We believe this is pretty cool stuff. You don't have to believe me, just fetch the latest Minix release, play with it, and see for yourself when you get a chance. This was actually research work we did here in the Minix group at the FU, work I did with Andy Chanavam and Anton Kausten. This research in particular was published at ASPLOS 2013 and received the Roger Needham Award and Dennis Ritchie Award by the systems community. So enough with the introduction, let's get to the actual problem we're trying to solve. Say that you have your computer up and running, and ideally you would like to keep your computer up and running all the time, but a software update advertising a new version of your favorite operating system comes in. So what you do if you want to install the update, you go to the typical update procedure. So you install the update, the new version of your operating system, you shut down your computer, reboot your computer, and then hopefully your new operating system version comes back online and you can continue working. This is all fine and all, but as we get more updates over time, we have to pay for a lot of downtime, potentially with disastrous consequences, as depicted on the slide. So, as it turns out, people have been aware of this problem for several years and are trying to devise solutions. So let's look at a bunch of common solutions people adopt in practice. Solution one is what we call spare time for downtime. Okay? So this is straightforward. You just bash all your software updates in predetermined and periodic maintenance cycles, and you somewhat get to minimize downtime. Now, the problem with this solution is that there are systems out there that simply cannot tolerate downtime at all, right? So think, for example, of industrial control or SCADA systems running a power plant, okay? So solution two is what we call roll your upgrades, okay? So this is also in widespread adoption. You can simply replicate your software installation across several machines, and then when there's an update, you can bump each machine to the new version until the system is globally updated. Now, the problem you have is that you have to deal with replicated state across several different machines, and you can have many different versions talking to each other during the update, leading to update time inconsistencies and perhaps subtle bugs. If you don't believe me, just ask the customers of a chemical bank who got detected around $15 million by mistake because of one of those update time state inconsistencies. Solution three is what we call don't patch, don't tell. This is also straightforward. Just keep your system running all the time, ignore all the updates. I know this is something many people do in practice, but it's a bad idea, right? So this exposes your systems to security attacks, and this is particularly bad given that studies show that as many as 75% of security attacks out there actually exploit unpatched systems, unpatched vulnerabilities and known vulnerabilities in unpatched systems. And finally, our solution, which we call live update, which is nothing but an instance of the famous aphorism from David Wheeler: all problems in computer science can be solved by another level in direction. Okay, so you can look at your running operating system as a running instance, say, of operating system version 1. Now, if we can bump this running instance to run operating system version, say, 2, then we can effectively deploy updates in a way that is transparent to both applications and users of the system. But that will usually create another problem, right? So now the challenge we have to solve, we actually have to solve a number of challenges. First, we have to devise a live update mechanism, a way to perform a switch over from version 1 of the operating system to version 2. Second, we have to determine a safe update state. So a time when it's safe to actually perform the switchover so that the system running the new version results in a consistent state for version 2 of the operating system. And third, we have to perform what we call state transfer, right? So we have the running version of operating system version 1 with its global state and data structures. So if we switch over the execution to version 2, we have to make sure that these data structures are transferred and transformed into a data structure format that can be understood by the new version 2 of the operating system. Okay, so how do existing solutions deal with all these problems? So a representative one is Oracle Ksplice. It's a commercial live update solution for the Linux kernel in this case. It's in widespread use. It's been used on more than 100,000 servers to deploy millions of live updates and counting. Okay? So Ksplice is what we call a hot patching live update solution. The way it works is you get a running instance of the Linux kernel, again version 1. Ksplice will freeze the execution of the kernel, will take a patch implementing an update, and will extract from the patch code and data changes from the update, and essentially glue these changes directly into the memory address space of your running kernel. Okay? So it will stitch all the code and data references to redirect the execution to the new version and just allow the operating system kernel to resume execution and execute version 2. So when we started this research, we looked at what kinds of patches can Ksplice and similar solutions support. Now, this is an example. It's a real-world security patch for the Linux kernel. You don't have to understand all the details here. What's important to note is that this patch is extremely simple and small. Okay? So just a couple of lines of code added to the Linux kernel code with no side effects to the global state of the system. Now, of course, this is an inherent characteristic of security patches, which are a killer application for live update solutions, but the problem here is fundamental. So next we looked at why that is that Ksplice and similar solutions can only support these small updates, small patches, and cannot scale to more complex updates. This really has to do with the way these solutions deal with the fundamental challenges behind live updates. So first, to identify a safe update state, they typically use an update agnostic characterization of safe update state. Typically, they forbid, for instance, update to running code. So if function foo is running, for example, they just forbid you to update and replace function foo in the kernel. Okay? The problem with this is that you still need to rely on extensive manual inspection. So patch inspection, as a user, you need to manually look at the patch and figure out if these patches can be glued into the execution at an arbitrary point in time. Okay? And this is error-prone and extensive manual effort. The second problem is the way they deal with state transfer, right? So all they do is automating very simple type transformations in global data structures. But if there is a more complex update, then you have to do everything manually. So you essentially have to code up your state transfer functions to transform your data structures from version 1 to version 2. Again, a lot of manual work. Finally, for the live update mechanism, as I mentioned, they use this hot patching strategy, which works and all, but the problem you have is that as you install more updates over time, you have these bits and pieces from many patches being stitched together in the same address space, causing memory address space fragmentation. So this in practice results in more performance and memory overhead over time as you deploy more updates on the system. Okay, so let's now flip page and look at what we actually want from our live update solution. So ideally, we would like to support arbitrary software updates of different natures, not just simple and small security patches, right? Second, we would like to ensure a safe and predictable live update process without resorting to extensive patch inspection. Third, we would like to automate complex tasks, such as state transfer and also what we call state checking the state for consistency at live update time, making sure that the live update process is as predictable as possible. Fourth, we would like to automate what we call hot rollback, essentially the ability to identify errors, to detect errors in our own live update or state transfer code. And if there is, say, crash in live update time, we would like the ability to automatically recover. So do what we call hot rollback, which is essentially switching back the execution to the old version, to version 1 of the operating system, and resume execution there safely. Finally, we want a stable live update process without memory address space fragmentation over time as we deploy more live updates. Now, to ensure all these properties, our live update design is based on 3 key principles. First, the adoption of process level updates. Now, we decompose our operating system into a number of processes, operating system components or processes. Say you have one here running version 1 of this particular component. Now, as opposed to hot patching solutions, which will install the update in place inside the process, what we do is when we switch, when we implement the switchover process at live update time, we switch the execution from process version 1 to process version 2. So this is a new process running the version 2 of the process. In other words, we replace entire processes rather than individual functions or individual lines of code, perhaps. Now, using this model has 2 immediate advantages. One obvious advantage is that we get rid of the instability of the live update process, right? So when we replace a process, essentially the new version looks like a fresh installation of the system. So you don't get memory address space fragmentation anymore, and whatnot. The other advantage is that we can dramatically simplify error recovery. So we can make sure we isolate our live update code and state transfer code execution inside process version 2. And exploiting the process sandbox, we can make sure that if there is an error during the execution, we just kill off of version 2 and to implement hot rollback, which is to switch back the execution to process version 1 and resume the execution there safely. The second principle is the adoption of compiler-based state instrumentation to automate state transfer and state checking. The way we do this is rely on the LLVM compiler framework to go from the original operating system component comprising some code and data into a statically instrumented version of the component comprising data, code, but also metadata describing the program state of the component. In other words, describing all the data structures and the pointers between them, comprising the entirety of the program state. And then we export this metadata information to a state management library, to our runtime system, essentially, which parses the metadata to do runtime state introspection and automate tasks such as state checking, state transfer across different process versions. Finally, we use what we call a controlled live update transaction. Essentially, once we've broken down the operating system into different components, we export a transactional interface to the user to allow the user to specify live updates and safety constraints. In other words, the user can say, I want now to update components A, B, C in a single transaction and in this predetermined order and with these update safety constraints. For instance, you can say the component B can only be updated when it converges to this particular safe update state. And we do this with what we call state filters. So state filters really look like assertions, essentially. They are conditions on the state and the data structures of a particular component to encode the safety constraints for the update. And we'll see an example. We'll look at an example shortly. So we implemented all these ideas in a research operating system prototype, which we call Proteus. This is its architecture. Surprise, surprise, it's a microkernel-based operating system architecture. Proteus actually was originally a fork of an old version of Minix. You can recognize the familiar design and architecture with a thin microkernel at the bottom, all the operating system components running as independent user-level processes. One difference with classic Minix is the adoption of this component, the update manager. This is the one component dealing with live updates, implementing live update transactions, and in particular, implementing the live update protocol, which synchronizes the different components at live update time to make sure we can support live update functionalities. In this particular example, we see the update manager interacting with the live update protocol, which is also based on message passing, with only one component. Here, it's talking to the old version of this component, and it's trying to convince the old version to be replaced by the new version of the same component, and effectively implement live update. So I mentioned that the live update protocol is implemented by the update manager, but the special thing about Proteus is that the live update protocol is actually tightly integrated in the life cycle and the programming model of individual components, allowing the components of the operating system themselves to actually cooperate and help out in the live update process. This is the way we do it. To enforce our programming model, we use an event-driven programming model you should already be familiar with. This is the typical event-driven programming model, which is also used in Minix. You might recognize the familiar structure. There's a main function, some initialization code, and then we jump to the top on event loop, where we fetch a message, we process that message, and we go back to the top of the loop to fetch the next message. Now, the special thing about Proteus is that the different stages in the life cycle of the component are clearly marked by calls to our runtime system to implement live update functionalities. In particular, there's an entry point, which in these days on Minix we call set startup. This is a call to our runtime system to inform our runtime system of the component-specific initialization code. This is the initialization code that we need to run to initialize the program state on a per component basis. When our runtime system receives this call, it will first talk to the update manager and ask, are we starting fresh? In other words, is this boot time? Is it the first time the component initializes? If the update manager responds back yes, then it will automatically run component-specific initialization code. But the update manager could say, no, you're a new version of the component, so we're actually starting up in phase of a live update event. In that case, our runtime system will automatically switch to performing state transfer operations and reinitializing the state of this component starting from the old version of the same component. So no matter what happens, once we're done with initialization, we jump to the top of the event loop. And our state is obviously initialized already, one way or another. Once we jump to the top of the loop, there is another special call to our runtime system that on modern Minix we call Ceph receive. So Ceph receive normally receives a message from the kernel as part of the message passing subsystem, but it also does something extra in Proteus. It intercepts special messages from the update manager, which are used to implement the live update protocol. In this case, the update manager could send a message to say, please prepare for an update. An update is about to happen, and you're about to be replaced. Now, clearly marking this call to the runtime system in a predetermined point during the execution is an interesting property of the Proteus design. In other words, in Proteus, the only possible update point, which is the only possible point where updates happen, is the top of the loop. This makes essentially updates as predictable as possible. Instead of happening at an arbitrary point of the execution, we know that the execution is exactly at the top of the loop every time an update comes in, and we need to replace the component with its new version. Okay, so this is an example of how we install updates on Proteus, and this looks very similar to what we do in these days also on Minix 3. Okay, so there's a special command line tool which we use in 3 invocations in this case, because we are trying to install a multi-component live update, in this case a 2-component live update. So we need a first invocation to specify the first component, another invocation for the second component, and the final invocation to just start up, issue the live update transaction, and allow the update manager to perform live update operations. In this particular example, we are trying to update the network server and the network driver in the same transaction, and we do this because this update actually changes the protocol between the network server and the network driver. So we want to update them atomically in a single transaction, and at the same time, we want to make sure that there is no interaction between the 2 components in progress. In other words, in Proteus terminology, this is a state filter. It's essentially a constraint on the safe update state, which we require for this particular update. And we simply express this with a condition on a global variable in the network server, saying that there should be no pending write. Okay? So as we issue the third command, this means we're ready to start the update. So our update manager will come back and say, I'm loading the 2 new process versions, I'm applying the changes automatically, cleaning up the old version, and live update is all done without any service interruption whatsoever. Okay? So let's now look at what happens in practice behind the scenes. And we'll do this from the perspective of the update manager. Okay? So in this example, we look at the update protocol essentially for a single component live update, which goes from process version 1 to process version 2. So as update manager, the first thing we have to do is load process version 2 in memory. Okay? And we'll leave it aside. Second thing we do is send a message, a special prepare message to process version 1, informing process version 1 that it's time to prepare for the update. The message will contain any state filters which are required for the update to happen. Our runtime system will automatically check the state filters and will detect when we're finally converged to a safe update state as required by this particular update. So it will come back to us and say, hey, I'm ready for the update. It's time to be replaced. So process version 1 is now blocked, and as update manager, we send an initialization message to process version 2. This message will cause version 2 to be activated and our runtime system to take over. Our runtime system will perform state transfer operations while the update manager traces its execution to detect errors and operate hot rollback operations if necessary. In the first phase, our state transfer framework performs what we call metadata migration. Metadata migration means copying all the metadata from process version 1 and from its address space in memory into the local address space in process version 2 where our code is currently running. Okay? At the end of this phase, we have all the metadata information we need. All the metadata information describing the data structures of version 1 and all the metadata information describing the data structures of version 2. So we can now interpret this metadata information, look up all the data structures across the two versions, pair up different memory objects, and transfer the state one object at a time in the second phase of state transfer, which we call state migration phase. Okay? So when the state migration phase is over, the state of process version 2 is finally reinitialized from its old version, and we can perform what we call control flow migration, essentially allowing the execution to flow from the update point in the old version to its update point counterpart, which is again the top of the loop in process version 2. Okay? So when this is over, our runtime system automatically sends an initialization ready message back to the update manager. So the update manager knows that it's now all okay, the update is installed, so it's time to clean up the old version and just allow the new version to take over the execution. Now, I'm not going to get into details of our state transfer framework and how it works because it's fairly complicated. I'll just give you an intuition with an example. Now, assume that the top of the slide is our program state in a single component live update. So we have a single data structure with some pointer into this data structure. Okay? And what you see on the left side of the slide is the representation of this data structure on an old version of the component, and on the right side of the slide it's its new version. If you look through the different fields of the data structure, you will see that we operated a bunch of transformations, right? So we dropped some fields, we added some new fields, we swapped fields around, we changed types of some fields, and so on. At the bottom of the slide, what you see is the representation in memory, the in-memory representation that our state transfer framework creates for this data structure. The way it does is that it parses metadata information during the execution. It will in particularly look up relocation information for both data structures, locating their address in memory across the two address spaces. Next, it will look up type information to associate a type and make sense out of the memory which belongs to the two objects, to the two data structures. Once it knows type information, it can reconstruct all the fields across the two versions within the two data structures, and it can also know where all the pointers are. So it can traverse the pointers and reconstruct the entire program state if necessary. Now, once it knows everything about these two objects, but also the rest of the state, it will just compare the two versions and automatically perform transformations and state transfer on the fly. So it will see that these two fields are the same and in the same position, so it will just copy data over. It will understand that these two fields are swapped, so it will copy data in their respective position. It will see that there's a type change here, so it will operate type transformations on the fly. It will realign all the pointers to reflect the changes in the memory layout in the new version, and it will also add the new field here and automatically initialize the new field to 0. Of course, this is our default state transfer strategy. For more complex updates, you might have to throw in some code to say turn a linked list into a hash table or something else even more complicated. And our framework supports extensions to do all that. In addition, I mentioned pointer traversal. So this is precise pointer traversal, essentially. So if you know a little bit about this, you know that doing this in C is extremely complicated. So we actually need some help in terms of annotations from the users. And you see two examples of annotations here. I'll now spend a few words before time runs out on the evaluation. We've actually tried the system with 50 real updates, around 15K lines of code, with only 300, and we did this with only 300 lines of state transfer code manually written. We had to also manually write 14 state annotations to support precise pointer traversal, and 4 state filters to support the updates. Just to give you an impression, the median patch size in our evaluation is more than an order of magnitude higher than K-splices, than the one used in K-splices evaluation. We've also measured the instrumentation cost to be mostly isolated in allocator operations and invisible in macro benchmarks, and the instrumentation to result in a relatively modest memory overhead due to metadata instrumentation. We also measured the update time. The interesting property of process level updates is that the update time depends on the amount of state you have, because the update time is essentially dominated by state transfer. So we did simple single component live updates here across all the components of the system, and we measured that even in the worst case, in the largest component with the largest state size, the update time was around 1 second or slightly less. Encouragingly, even doing this across the whole system, so we could in fact implement a single live update transaction which replaces all the operating system components with new versions. Even in this case, the total update time was actually 3 seconds. Now these numbers are pessimistic because we've actually improved the update time and the state transfer strategy in the past few years. Anyways, so even 3 seconds to update in the worst case scenario, replacing the entire operating system with a new version is quite realistic, given that updates are relatively rare events. And the only disruption that you encounter on the system is that essentially you cannot serve system calls during an update, but the system call processing in user land will just be delayed for a few seconds every once in a while. So to conclude, I presented Proteus. This is a research operating system completely designed with live updates in mind, and all the changes I've described during this presentation are finally integrated into the MINIX3 release. I showed you how our design can support several classes of updates with relatively low effort in practice. I showed you how we give user full control over the live update to transaction to ensure the maximum predictability and safety of the live update process possible. I showed you how our process level updates can ensure a simple and stable live update process, no matter how many updates you actually deploy in the system, and how we can automate and give support for extensions for complex tasks, such as state transfer and state checking. And finally, our support for hot rollback, which is capable of detecting and automatically recovering from errors in our own state transfer and live update code. Okay, so this concludes my talk. To take questions. Yes.
Okay, well, I would like to ask 2 questions. First, how is your update manager upgraded reincarnation server? If not, what's the relationship between the two?
So in modern Minix, you will find the update manager integrated in the reincarnation server. So I think we kept the original reincarnation server name, but now it does many things, not just reincarnation, including updates.
Thank you. And the second question is, okay, so you were updating the service. Right?
Yes.
What about the kernel? Is that even being considered?
Right. So the one thing I forgot to mention, so this was sort of implicit, we can update all the system services, so all the core operating system components, including the update manager, or today called the reincarnation server itself. So the reincarnation server can basically update itself. So using the same tricks which we used for the reincarnation server, in principle, on paper, essentially we could support the same tricks and the same updates for the microkernel. but this hasn't been implemented yet. So this would be a cool project, but we haven't done this yet. Yes.
Have you also updated a lot of drivers that way? Because drivers, you also normally have some unfortunate hardware memory and time issues on the hardware memory. There, the update process might be, if it's the right time to do the update, might need to unlearn something about that.
Yes, so we've done that even in modern Minix. We have, so I haven't touched much on this, but our live update protocol essentially supports this notion of save update state. And we typically do this with state filters, so they can be evaluated on the fly. But you can also code up support for custom safe update states in the component itself. So the driver can export some well-known states which are relevant for drivers. And more, to expand on that, we haven't focused too much on drivers. So these are all, the drivers are all supported, but the state management issues which I described here are only partially relevant for drivers. So there's some drivers which are essentially pseudo-stateless. You can just kill the driver and have the driver get replaced by the new version, so you don't have to deal with state transfer often and things like that. It's actually an interesting thing because, and I haven't discussed this at all, but basically in Minix now you have more complex state management policies than what I presented here. So depending on the component, you might want to transfer the state, you might want to restart fresh, and this is all policy driven essentially in the recent release. It really depends on the component. Our focus here was mostly on dealing with state. So this is mostly relevant for system servers. So think of process manager, the memory manager, and so on. Yes?
In the ASPOS paper, you mentioned that this is also valuable for security because you can change processes on the fly, so malware that expects to know the layout sort of can't figure out the layout, or sort of address-based randomization done large. Do you know if that's in the 3.4 release?
This particular feature, David? I think so. Okay.
We have ASR support.
Yeah.
So it's in there. So it also has security value in addition to this other.
Absolutely. Maybe we should mention it's not enabled by default, so you actually have to install or actually compile the system in a special way right now for other reasons. We're still working on the integration, but if you compile and set up the system this way, then yes, you can do it.
So it gives you much stronger security than most systems have.
So I haven't had time to mention actually all the extensions. So yes, we use live update to also do live randomization and get stronger security. We've also done, this was 2013, so we've done a lot of follow-on research. We've extended this to user land, so we can now do user applications, live update if you want, but not all of that is yet, and there's ongoing research of course on some of these things, but not all of that is integrated in the release. So, but these two things are already in there. So for everything I described in this presentation, plus security applications of live update, in particular live randomization. Thanks for mentioning that. Yes?
If I may go back to the state filters, which, if I understand them correctly, they somehow define the safe state where the update can be done.
Right.
What about the situation where there is no such safe state, where the servers are constantly communicating? Do you have some strategies for that?
So it's possible. So like when I gave this talk at ASPLOS, so the question was formulated in a different way, but it's essentially I think the same question. The question was, can you update your Minix system into Windows or Linux, right? In a single live update. So this is essentially the same question. I mean, the way I answer this question is, we're essentially providing a framework here, right? So we have all the building blocks in place. You can do state transfer and you can register your own extensions. You have live update transactions, you have state filters. In other words, we export all the relevant abstractions for the user to do very little work to reason over update safety, transform data structures and whatnot. But this is still a framework. You want to do Minix into Windows or even more crazy updates, in principle it's possible. There's nothing fundamental here. But you have to find a way to basically code up this kind of update using our abstractions, which we believe to be much more powerful than, we install an update in a random state of the system and fingers crossed, right? But you still have to put the effort to express the update using our abstractions.
Isn't it also a security risk, actually? So I think you also...
They're always a security risk.
Yeah, because you describe the state of a service, basically. So if you hijack a service, then you know exactly what to prevent the next update. So is that perhaps a risk, or...?
So you mean the metadata information could leak information about the state of the component?
Well, suppose, so for example, if you want to prevent zero-day leaks, so but suppose the service is already hijacked,
Okay.
then you can prevent an update by changing the metadata that's already in the...
So you mean so a component is already compromised and basically you can prevent updates? Yeah, so the idea is you make sure that your system doesn't get compromised. Once it's compromised, you have a problem. But you have a problem whether you're supporting live update or not, I think. So it's
Well, so the idea is that if you are compromised and you do an update, then you're good again, right? That's why you're...
So yeah, keep in mind that the update protocol is cooperative. So the attacker can just say, you know what, I won't cooperate. So yes, so you have a problem. But there's a compromise there. We don't want to support cases where the system is already compromised, I think. So there has to be some manual effort there in doing the recovery, just healing the component perhaps. You cannot go for a cooperative approach if that answers your question. Manolis, I guess you have a question?
I'd like to ask, can you skip an intermediate update, or you have to go from N to N+1 version?
Oh yeah, that's a good question. Yeah, there's nothing preventing you from going again from Minix to Windows or skipping intermediate updates.
So is the state transferred in a serialized format?
Right,
that
so
is independent of the version?
Exactly. So a state transfer, you can look at state transfer as a mapping between version 1 and version 2. What version 1 and version 2 represent is essentially up to you. You can go from 1 to 10, or you can do 1, 2, 2, 3, 3, 4. The balance there is whatever is easier, right? So you have to perhaps provide. So if the state transfer framework and the default transfer strategy does what you want, it doesn't matter. Right? You can just allow the framework to do whatever you want.
It's up to the new version.
Right. Yeah. Both strategies will work. But in practice, if you have very complex updates and you have to go code up some state transfer functions, then you have to redo it again, right? So you have to go, version 1 and version 2, and incrementally to version 10, and code up these intermediate steps, and then you also have to implement the whole thing. But you can perhaps reduce code because the transformations, the cumulative transformations are essentially the same. Yes?
Do you have some examples of systems that use live update? You might know about.
Examples as in out there production systems?
Yeah.
So, I'm not sure, maybe I was too fast on this slide. So on the case slide. So these are statistics, actually relatively old, I think, statistics. Maybe they are new. This is 2013 from systems using Oracle case plans. This is the Linux kernel, of course. But you can see here that it's in wide use. So 700 companies, more than 2 million live updates. So they're not open about their customers, but I suspect that they have a lot of companies interested in these kinds of technology.
From kernel version 4.0, it's already in there. The kernel live updates.
But it's not case-by, it's K-graph. It's different project.
Yeah, so now they have basically open source case plans. So
It's not,
if you look,
it's not space-by.
yeah. So what I meant to say is that the design is pretty much the same. So it's a hot patching strategy. They have slightly different things, but it's now in the kernel. Yes.
I would disagree about the internal.
Yeah, depends. So to me, if it's hot patching, it's the same. So that's in the scope of this talk. If you want to talk details, yes, it's not the same.
But really, it is not. That they also. It's not so
Yes, it's not.
as your project,
I
but
agree.
they also support various state transfers using the RCU implementation for keeping the stale data for the instances that they are still using the stale old data and the new code running on the new data. So I would not dismiss it as totally.
I don't mean to be dismissive. In fact, I think case plies, and derivatives are actually very cool projects. So if you want to support relatively simple patches, they work quite well, right? So
Yes, again, I would reiterate, K-graph has nothing to do with case plies. It's a totally different implementation
Right.
based on.
We agree on that. So we already agreed on agreeing on that. Yes.
Yeah, because sorry, to finish the really wondering about the application of this kind of technology, because the space flight is really targeted to these micro patches that really...
Security patches, which is, you know, obviously a killer application of live update.
Anything beyond that, I mean, if you build a high availability distributed application, you have to anyway worry about nodes dying, right?
Right,
So it can be perhaps easier to bring them down one by one and then bring them back up running a new version, potentially a new kernel.
Yeah, this is essentially rolling upgrades. Yeah, so these are in widespread use, and the question is, if you already have a distributed systems of some kind, do you need this technology? But in many cases, you have systems which do not need replication, or in fact, when you do replication, you have to deal with replicated state, which is not always easy to do, and you can introduce inconsistencies. Yeah, in some scenarios where you already have a distributed system, in fact, even the systems community has looked at many solutions to do live update on a distributed system scale. Not just rolling upgrades, but even do something more complicated. So here we're mostly in a scope of a single system. If you have a single instance and you want to update that single instance without using replication necessarily, what do you do? That's the target, essentially. Yes?
So maybe you know that the deployment system for Oracle Solaris is called Live Update. But as far as I can tell, it's a file system image-based thing that has nothing to do with the
Yeah.
process.
So this is very unfortunate. So if you look at the terminology in the research community, it gets even more confusing. I can mention 15 names for this very same thing. The official name in the software engineering community is Dynamic Software Update. It's not short, it's not pretty, so we use live update mostly in the systems community. But yeah, it gets confusing because the marketing guys also like to call everything live update, so it could get complicated in some cases.
Oh, there's real life.
Live update.
Okay, I think that was it. So then now we have another break, and then the next session begins at 3:30.